Hello, 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 how are you? Hi. Hello, friends. We were in middle of discussing the rules no, that help us to obtain the root locus from the open loop transfer function of a given system. So when we are at here rule 7 that tells us about angle of departure from the open loop pole. Let us quickly review it and understand how to determine the angle of departure for the root locus branch that originates at no any pole. Here we are talking about the complex pole, right, shown by cross here. Now we have for us a point S naught, right? This is the point of interest S naught in close proximity to the open loop pole. Epsilon signifies that no the distance between S naught and open loop pole is very small in the limit no epsilon tending to what 0. So uh, whatever will be the angle theta 1 that will come out in this case, right? The angle subtended by this pole, complex pole at S naught, will be the angle of departure because the point S naught is in the vicinity of the root locus. And if S naught satisfies the angle criteria of root locus, then S naught will very much will lie on the root locus, and the line joining the open loop pole to S naught in fact will give us the angle of departure of the root locus branch at a given no, open loop pole where no branch originates for k equal to 0. So we have seen in our last class we have here uh, three poles, right? These two are the complex pole, right? This is pole, let us say P1, it's accompanying conjugate P2, and you have a real pole lying on negative real axis P3. You have one zero Z1 on real axis, another complex zero Z2, right? So we know the angle criteria of GSHS uh, for any point to lie on no root locus. The angle subtended at that point S naught by the open loop transfer function GSHS should be a odd multiple of 180 degrees, right? This is the condition which we know have available for us from the angle satisfaction, right? Angle criteria. Now, quickly, if we see the angles, right, made at S naught by the open loop poles and zeros, we will get something like this. Let us collect for zeros. The angle made, one is Z theta 6, another is theta 2, and for remaining and for poles, not remaining, for poles, the angle made at S naught will be plus in bracket minus yes, it will be theta 1. There are three poles, right? Then minus theta 5, right? And theta 5 is this angle, right? And minus theta 4. Now we can say that for all other uh, open loop poles and zeros which are joined to the point of interest S naught, their angles no subtended at S naught are as good as the angle made by these factors at the open loop pole P1 itself, because P1 and S naught are so much close to each other, they can be taken as the same point, right? So angle contribution will make hardly any difference when we put this limit where epsilon tends toward 0. So in this case, angle theta 2, theta 4, theta 6, theta 5, they are the angles made by other open loop poles and zeros at the open loop pole P1 itself, though they are actually no angle made at no point S naught of interest, but because of its close uh, proximity, right, in the immediate neighborhood of the pole P1, we can say these are also the angles made by other open loop poles and zeros at the pole P1, right? In that case, we know sum of all these angles have to satisfy the angle criteria, that is plus minus 180 degree, and no, some odd multiple of this 180 degree, where q runs from 0 to any integer. So in this case, for me, let us say I want, uh, yes, in which angle I'm interested in, angle uh, theta 1, right? Because theta 1 will give me the angle of departure, right, as the root locus branch moves leaving the open loop pole at p1 for higher values of gain k. So theta 1 for me, I can very well write down this as equal to, I can take theta 1 on other side of equation, and then on this side of equation will be theta 6 plus theta 2, right? Then it will be what? Minus in bracket, I will now put theta 5 plus theta 4, right? And plus minus 180 degree, right? Because since it is plus minus, when I take it on that side, it will remain plus minus only, right? 180 degree into 2q plus 1, right? So that is what we see, or more precisely, as no, in a sophisticated way, the angle of departure is mentioned here, no, in this place that I have just encircled. So that angle of departure is theta 1 for me here in this discussion. So it is equal to 180 degree of 2q plus 1 plus 5. So you can see this phi is nothing but the angle made at the open loop pole where we wish to find out angle of departure of the root locus branch. So this phi is the net angle subtended by all other open loop poles and zeros at the open loop pole where we are interested to know in what direction and at what angle the root locus branch will leave it. So in this way, it will come out to like this. Phi will be given by nothing but this summation terms, right? Sorry. So in this summation, the angles made by open loop zeros would be positive, since zeros are no in the numerator of the transfer function, and in the summation, angle made by the poles, that will be contributing negative, right, since they are in the denominator of transfer function. So the same thing which we discussed there in the last class, but we have here now summarized it, right? The angle of departure can be found out with this particular expression, where phi is the net angle contributed at the pole by all other open loop poles and zeros, right? So we have seen this in our last class, and we have now summarized that into a relation expression that is given here, right, under rule 7. So that talks about angle of departure. In similar way, we can also talk about angle of arrival, right, at a open loop 0, right? So when we do the same mathematics which we did by considering a point of interest S naught in the close vicinity of the 0, right, at which we want to know at what angle the root locus branch would be arriving, at it, would be terminating at it. So we consider S0 in proximity of one such open loop 0, and we join that point S naught with all open loop poles and zeros and find out what the angles contributed by respective poles and zeros at point of interest S naught is. And again, we say all these angles except theta 2. What is this? This is theta 2, right? So there appears theta 2 twice here. So let us say this is theta 1 for us, right? Theta 1, theta 2, theta 3, theta 4. Yeah, let us say this is theta 1. So in this case, we know all the angles, right? Like theta 1, theta 3, theta 4, theta 5, and theta 6. All these angles except theta 2, we say are as good as angle made by no other open loop poles and zeros with the open loop 0, at which we are no interested to know the angle of arrival of the root locus branch, because the point S naught is so much close to theta 2 under the small separation epsilon that tends to 0. We can say these angles are as good as angles made by the respective open loop poles and zeros with the open loop 0, right, where we are interested in. So same thing when we do, we say the angle of arrival phi z, right? Here it is given phi z would be now given by this particular expression, right? In angle of departure, it was plus phi. In angle of arrival, it will be what? Minus phi. So that's what we will be ending up with in finding out the angle of arrival of root locus branch at a open loop 0, where the branch is likely to be no terminated. So here quickly the example again which we have initiated last discussion. Quickly look at the concept of angle of departure here. Uh, so with our discussion, we know that angle of departure is given by angle, angle, let us say phi p, that is plus minus 180 degrees of 2q plus 1 plus phi, right? So what is this phi? Yes, I am interested in knowing what is this angle phi, right? So angle phi can be obtained by joining no all other open loop poles and zeros to the open loop pole at which we are interested in. So here we have in total three open loop poles, two complex poles and one real pole and one real zero. So when I join them with the open loop pole where I am interested in knowing the angle of departure of the root locus branch, right? So from our earlier discussion, we will have three root locus branches corresponding to three open loop poles, each originating when gain k is 0 and branch grows with no higher values of gain k. So this angle phi here will come out to be what? The angle subtended at the pole P1, let us say this. So this angle made by this pole, that is theta 2, in our summation will be minus because it is from a pole. This angle theta 4 in our summation will be minus because that is also from a pole, while this angle theta 3 from a 0 will be what? Positive in our summation. So quickly let us put down the values. Theta 2 we know will be 90 degrees, right? Theta 2 itself is not minus. Remember the angle contribution, right? In by GSHS, right? At P1, right? That because of this pole comes out to be minus, since the pole always are in what denominator of the transfer function. So this becomes minus 90, then minus, then theta 4. Theta 4 will be tan inverse of 1 by 2, and tan inverse of zero point 0.5 we have seen last time is something 26.56 plus theta 3 is tan inverse of 1 by 1, that is 45 degrees. So when you do this summation, it comes out to be minus 71.56, right, degrees. And now when I find out angle 5p, the angle of departure of root locus branch at this particular pole, it will be something 180 degree, right, minus 71.56, right? This is minus. So I can take either here plus or minus. I will end up at the same point. It does not matter, right? So if I take plus, my answer will be close to 108 to 109 degrees, right? And if I take minus, it will be how much minus, then if I take minus 180, I mean, then the summation here will be minus 251 degrees, right? So if you look here, minus 251 degree means you are moving in this direction, right? uh, Clockwise direction, and somewhere here you will be, right? So this will be minus 251, and 109 plus 109 will be what? You are moving with positive real axis in counterclockwise direction. You will cross the no 90 degrees line. This is 90 degrees line, so you will cross that, and somewhere here will be 109 degrees, right? So this and this will be what? Same. The point where you will lie, right, on the straight line, that will be a same straight line, right? Whether you draw with minus 251 degrees or plus 109 degrees, right? So that's what we see. The angle of departure theta 1 here comes out to be 109, close to that, and you can draw that, and you can root locus branch leave parallel. Initially it will be parallel to what? The 109-degree line, and then it just goes on, following the asymptotes. So here we have not shown asymptotes, right? But if we work out asymptotes will just move parallel to your y-axis. We have seen in our last class minus 90 and minus 270. I think we have two asymptotes. The angle of asymptotes will be given by angle phi a, and that will be how much, friends? 2q plus 1 into 180 degree by n minus m, right? So n minus m here is 2, 3 poles, 1 0. So 180 by 2 will be 90 degrees. 90 into 2q plus 1. And as q starts from 0 and ends at n minus m minus 1, it will end at 1. So this will be angle phi will be for q equal to 0, it will be 90, and for q equal to 1, it will be what? 270. So you can see there will be two asymptotes, right? Let us say centroid is here. So this is 90 degree, right? And let us say another is at 270. So this will be 270. So one root locus branch goes parallel to this asymptote. Another root locus branch goes parallel to this asymptote. That's how the root locus branch would develop, right? And here your system remains asymptotically stable, as we see for all values of gain k. Here as root locus branch uh, goes to infinity for k equal to infinity. Similarly here the root locus branch, right, it goes to infinity for k equal to infinity. It always remains in the left half of the S-plane and never bends and crosses the imaginary axis and tries to enter in the right half. So you have a asymptotically stable system for all values of gain k from 0 to infinity. System is what? Always stable. So that's what about this particular example which we had. Now moving on to next rule. uh, we have seen it no before in some of our discussion, which we are calling here as rule 8, the point of intersection of root locus branches with imaginary axis. So we had some time before, if you remember, one example of open loop transfer function like this. You had I think three open loop poles, right? And so what were the asymptotes here? Asymptotes would be what? 180 degree divided by what? N minus m. So it will be 3 into 2q plus 1 when there are no zeros, right? So that is 60 into 2q plus 1, and we get three asymptotes, 160 for q equal to 0, 180 for q equal to 1, and another 300, right? So somewhere, let us say, we know the asymptotes will be giving this directions. So you have this branch that originates at k equal to 0 moving to infinity with k equal to infinity, and these two branches that originate at two open loop pole at k equal to 0, they face each other, and at some point they break, one moving here and another moving parallel to this asymptote, right? So that's how we get the root locus develop. And we know that in this case the root locus branches are moving into the right half of the S plane. So rule 8 tells us about finding out the intersection of root locus with imaginary axis. And earlier also we have made use of Routh criteria in determining such intersecting points between the root locus and imaginary axis. We will quickly take an example here also to fine tune that concept and rule 8. Next, in rule 9, uh, it tells about now determining gain k at any point s naught on the root locus. So if I want to know that, we know root locus, as in this example, tells us all possible values of the closed loop poles or the roots of the characteristic equation with respect to variation in gain k, right? From 0 to infinity. Now, as k is varied, the root locus develops like this. Now, I want to know at particular point, let us say at this particular point, S naught. This is the point of interest for me, S naught, that what is the value of gain k here. For finding out gain k at point of intersection with j omega axis, we fall back on the auxiliary equation in Raoult's array we have seen in last discussion. But at some other point, right, general point in complex plane outside the imaginary axis and real axis, if I want to know at what is the value of gain k here at this point, right, where that falls on the root locus, for that what I will do, I will join that point s naught with all open loop poles and zeros. So that's how I have joined here. Then I have three phasors. D1 is the phasor length of the phasor joining at pole at origin to s naught, and let us say this is what given by d2, and this uh, phasor, right, is given by what d3. So I would have k as product of phasor lengths from open loop poles to S0. So D1 into D2 into D3, right? Divided by product of phasor lengths from S0 to open loop zeros. In this case, there are no zeros, so it will be only 1, right? So I can find out gain K at any point on the root locus by finding the phasor lengths of respective open loop poles from the point S naught, and then taking the product of those phasor lengths, right? For poles, the phasor lengths product will be in numerator, and the product of phasor lengths from S0 to open loop zeros will be in denominator. This value of gain K, which we are talking, comes from the magnitude criteria of root locus. The magnitude criteria tells us magnitude of GSHS at any point S naught should be equal to what? 1, because the criteria that events identified is for points to be on root locus, GSHS should be -1. This was further broken into two criteria: magnitude criteria, that is given that magnitude at all points which are potential to be on root locus, the magnitude has to be 1. And angle criteria is angle GSHS of all those points which are no which can potentially be on root locus. It should be a angle should be a odd multiple of what 180 degrees, right? So this is how we had two criteria. So the gain K that we are finding out at any general point on root locus outside imaginary axis and real axis is developed by making use of angle criteria. When angle GSHS is equal to 1, then we know we can always take magnitude, and the magnitude of it will be K into mod of product of no what should I write? All uh, poles. Sorry, it will be what? All zeros, right? Uh, Divided by the magnitude of product of what? All poles, right? If I'm taking at point S naught, S will be S naught. So it will be Pi, let us say. So this magnitude should be equal to 1, right? Or let me make some space here. It's so what we were talking about, finding out gain K. Here, when we put the make use of this particular no now relation, where using magnitude, we know magnitude of product of all terms divided by magnitude of product of all denominator terms. This will be equal to 1. Then from this K will be equal to what? This will go on to numerator on this side. So it will be product of magnitude of product is as good as product of magnitude, right? Because finally we are interested in magnitude, right? So product of magnitude of S naught plus Pj, right? Let us say we are characterizing the factors as no j for poles, j equal to, here I wrote I, right? So let me keep I only instead of confusing. Let us say this is I. So this is I equal to 1 to n divided by product of magnitudes of term S naught plus z j, right? Where j runs from 1 to m, right? That's what we saw here. So but here it's the poles are taken as j. You need not be confused, right, with this suffixes. Okay, it can be j or I. So we have a product of all phasor lengths of pole in numerator, product of phasor lengths of poles from the open loop from the point, right, potential point S naught to product of phasor lengths of open loop zeros from the point same point S naught. So that's how we can find out the value of gain K at the point on root locus. So now we will quickly look into one example before we conclude with root locus and start with Bode plot or Nyquist criteria. So friends, here is a small example. open loop transfer function of a unity feedback closed loop system is given to us. So we need to find out, or rather construct the root locus for this given open loop transfer function. So as we know, our step one will be to obtain the all possible open loop poles and zeros. There are no open loop zeros. Total there are 2 plus 1 3 plus 1 4, 4 open loop poles, right? One open loop pole is at origin, another open loop pole is at -3. So let us say this is -3, and factors for this s1 and s2 will come out to be minus b, that is -2, plus minus under root of b square, that is 4, minus 4ac, that is 8, by 2a, that is 2. So it will be it will be -2 plus minus j, right? Negative under root will be j, and under root of 4 will be 2 divided by 2, or it will be equal to -1 uh, plus minus j1. So you have, if here you have somewhere -1, and let us say here you have j1 length, this is minus j1 length, then you will have something like this, right? So when you have one pole will be here, this pole will correspond to -1 plus j1, and one pole will be here, this pole will correspond to -1 minus j1, right? So you have got the positions of all open loop poles of the transfer function. So there will be total 4 root locus branches, each starting at a open loop pole when k is equal to 0, when k is equal to 0. Here it starts with k equal to 0. And we know that, yes, this region, right? This region on the root locus will be part of, this region on the real axis will be part of root locus, since there is only one open loop pole on the right side of the points between 0 and -3 on the real axis. So this branch will move in this direction, this branch will move in this direction, right? So somewhere here there will be breakaway point. Let us see where will be the breakaway point. So what we do here, we have got all the branches. So let us quickly determine the breakaway point. So for breakaway point, we make use of characteristic equation. Uh, we know that it will be 1 plus gs hs equal to 0. Now this will be giving us, equation with k, like we have seen it earlier. It will be no it will be s into s plus 3 into s square plus 2s plus 2, right? Plus k equal to 0. Or you can get the value of k from here. K will be equal to what? Yes, all these things will go on that side. It will become minus s into s plus 3 into s square plus 2s plus 2. Now you can open the brackets here, and can get a no expanded form, a polynomial form. It will come out to be something like this. It's in here solved for me in my book. It will be minus in bracket s to the power 4, right? Highest term will be s to the power 4, s to the power 4 plus 5s cube. So it will be 1 minute. Yeah, it it will be somewhere here. Can I write? Yeah, s to the power 4. Then I have plus 5s cube plus 5s cube. Then I have plus 8s square plus 8s square plus 6s, right? So I have this k now in terms of s, and now I can differentiate k with respect to s and equate that to 0. When I evaluate that, I will get some values of s, right? And here I am getting the possible values, three possible values of k, because derivative of k equal to 0 comes out to be a third order equation in s, giving three possible values of s. One is real, minus 1 by there will be three possible values of s. One is real, that is minus 2 by 3, minus 2, minus 2.3, sorry, yeah, minus 2.3, and another is a complex, another two are complex, minus 0.725, minus 0.725, plus minus j 0.365, right? You can find out this with your calculator. Three values of s have come. Now you know which can be the likely candidate that qualifies the breakaway point. Since the two branches are on real axis, so naturally somewhere on real axis only they will meet, collide with each other first. So the point on real axis at which they meet in these three candidates, this only is eligible, satisfies. So we label this as our what? Breakaway point. This is the breakaway point at which the root locus branches will know for one last time meet on real axis, and for further increase in gain k will leave, depart real axis. So let us say somewhere here is minus 2.3. So the two branches will come up to here and then they will move, and they move all here we see all the four branches will be no guided by four asymptotes, because there are no open loop zeros, finite zeros, where the branches can go and terminate, end themselves. So becomes interesting to find out no angle of asymptotes. Here there will be four asymptotes. It will be given by 2q plus 1, right, into 180 degree divided by n minus m, which is 4 here. And we know q will run here from 0 up to what? N minus m minus 1, that is 3, 1, 2, and 3. Up to 3 it will run. So for q equal to 0, anyway 180 by 4 will be how much? It will be 4 180 by 4, right? It will be 4 4 are 16, 20, 45, right? 45 into 2q plus 1. So for q equal to 0, it will be 45. For q equal to 1, it will be 3 into 45, 3 5s are 15, 12 plus 1, 135. For q equal to 2, it will be 5 into 45, 5 5s are 25, 5 4s are 20, 225. And for q equal to 3, it will be 7 into 45, 7 5s are 35, 7 4s are 28, 315. So like these four angles, asymptote angles you will get. And the likely centroid of asymptote, right, minus sigma a, that we find is from equation no sum of real parts of poles minus sum of real parts of zeros divided by n minus m. There are no zeros here, so quickly you can find out the center of asymptotes where all the four asymptotic lines meet on real axis. This will be always on real axis, right? Asymptote. So since all are real terms involved here, so real parts of poles, what we have, two complex poles have real part given by minus 1. So it will be minus 1 in minus 1 minus 1, then minus 3, right, divided by what? 4. So it is minus 5 by 4 and will be equal to minus 1.2 something, right? 1.25, let us say. So somewhere here will be the centroid of asymptote, right? Somewhere here will be the center of asymptotes minus sigma a. So draw the lines. This is 45 degrees, right? This is 45 degrees. Then this will be how much? 315. Then you have one is 135. So this will be 135, right? Then 225. So like this they will go, right? 45, 135, then 225, and then 315. So you have four asymptotes. Now these two branches, right, they will meet here at minus 2.3, and one branch will go along this, another branch will go along this asymptote. So this is how root locus will move, right? So this is one branch of root locus, right, that follows the asymptote, this asymptote. This is another branch of root locus that follows this asymptote, right? The root locus branches will move parallel to the asymptotes, right? Then these two asymptotes are also there along this. These two branches will move. So these two branches are originating at no open loop, complex open loop pole. So let us find out what is angle of departure for this no pole at minus 1 plus j1. So that pole is at minus 1 plus j1. So for this pole, let us find out the angle of departure, that is given by phi p. So what you do, I should little clean the space here, otherwise it's very difficult for you to understand with my writing making it more difficult. So let me pause a minute. So I have redrawn the open loop pole zero no locations. Now we have to find out angle of departure at this pole, right? That is minus 1 plus j1, right? This is minus 1, right? Real axis intercept, imaginary is j1. So what we do, we join this pole with all other open loop poles and zeros. So here it will go like this. This pole will make an angle of theta 1 there. This conjugate companion will make 90 degrees at that pole, and similarly this pole will make an angle of theta 2, let us say. This is minus 3. So what will be theta 1? Now we don't have no graph paper before us, but we know this length. So what will be this angle? If this angle is, let us say, phi, right, just for namesake, then phi will be given as what? Tan inverse of this opposite is 1, adjacent is 1, tan inverse of 1, right? That will be 45 degrees. And this angle will be 180 minus 45. So theta 1 will be equal to 180 minus 45, and that is 135 degrees. This is 90, and this we have to find out here. This will be how much? Tan inverse of opposite, that is 1, by adjacent, that is 2. So theta 2 will be given by tan inverse of zero point 0.5. That is from our last discussion, 26.56 something, right? Degrees. So now how to find out angle of departure phi p at the complex pole minus 1 plus j1, right? That is to use the no expression which we have seen in the last rule. So let us quickly put it. Let us sum up all the angles first from other open loop poles and zeros. So, so here for me the angle phi, that is sum of angle at minus 1 plus j1 by other open loop poles and zeros is theta 1 is from a pole, so it will be minus 135, Always I'm measuring angle with positive real axis, remember friends, right? So then theta 2 is, I have found is 26 again from a pole, so it become minus 26.56, and this is 90, right, from its conjugate companion. So sum of all this will come out to be how much when we look at it. Yes, uh, yes, wait a minute. Resume. Yeah. So this now comes out to be, on summing up, uh, minus 251 something, right? Minus 251.56 for that matter. This is the total angle made at minus 1 plus j1 pole by remaining poles and zeros. So angle of departure phi p would be 180, right? Plus this, that is minus 251.56, right? This is minus, ink is spreading so much, I will try to write slowly. So when you sum it up, you get minus how much it comes out to be, minus 71, right? Yeah, minus 71.6, it comes out to be minus 71.6, something like that, close to that, 71.6. So this is the angle of departure at the pole. So where will be minus 71.6 degree? So here you will draw it like this something, right? Minus means you will measure in clockwise direction, right here. So the angle of departure will be following this line. So this is the pole, so it will move parallel to that, no, minus 71 at an angle of 71.56, and then it will follow this. So it will leave here at this, and then it will follow the asymptote, this asymptote, right? So this branch will move parallel to this asymptote like this, and symmetrically, if this is leaving at minus 71, this will leave at plus 71. Plus 71 will be somewhere here, right? Okay, this is plus 71 degrees, so it will move like this branch, and it will then bend and follow what, the second asymptote. It will move along this asymptote, right? It will move parallel to this asymptote. So to show you a clean root locus here, you have one pole here, one pole here, one pole here, and one pole here, right? So then you had four asymptotes, right? At 45 degree. So you had asymptote something like this, right? You extend it here, it comes out to be like this, then like this, then like this, right? So yeah, it should actually join same point. So these two branches, they break a real axis somewhere here, right? So this, it goes like this, right? And this branch that lives here moves parallel to this branch lives here and moves parallel to this. So you, in this way, you have the four branches moving. This is one branch, this is another branch, right? So you have four branches, all four, they are moving to infinity in different directions, right? The direction of no movement is given by the four asymptotes, right? So in this way, see, this way we see that these two branches, they never move into right half, but these two branches which originate at these two complex pole, they enter the right half after no certain value of gain k. Now here it remains to determine what the point of intersection of the branch with imaginary axis. For that, we will fall back on Raut array as we did last time. We will make Raoult's array, and for some value of gain k, we will get all zeros row, and above that we will have auxiliary equation, construct that, right? Differentiate auxiliary equation, equate to zero, and the solution of dA of S by ds equal to 0 will give you point of intersection with imaginary axis. So I leave that as no exercise for you. And on substituting that S naught in no expression for gain k, which you have already in terms of that range of S, you will get the gain k at which the root locus branches intersects the imaginary axis. So let us stop here.